Hey everybody, thanks for that great introduction. So I'm going to be talking about visual effects. So I'm kind of curious, how many visual effects or animation people do we have in the audience? It's a sort of a smattering. You know, I kind of expected about this amount, but don't worry. I'm kind of talking in broad terms here, so to try to keep it interesting for everybody. So let's flip through here. Introduction. Luma Pictures is a visual effects company based in Santa Monica and Melbourne, Australia. So we have two different locations, and we make the pretty pictures for all the big feature films that you've seen. And on a scale of 1 to 10,000, which is about how big the biggest visual effects companies can get, we're 140. So it's pretty small when you think about it. And in order for us to be able to compete and stay nimble, we have to, we really feel a need to punch above our weight. We have to adopt the latest technologies and things that we think are going to be transformative in the industry. And one of those things, obviously, is the cloud. But in visual effects, we have a handful, a number of complex challenges that have to be faced in order to distribute our computations into the cloud. And those are the things I'm going to be talking about, some of the things that I think are unique to our industry, and maybe Luma in particular. But I think that there'll probably be a lot of similarities maybe that you'll find in your own. Now, one of the big reasons that people like me get invited to talk at things like this is because of the eye candy. And I'm not talking about this. I'm talking about our demo reel, right? All the things that we work on for Marvel and DC and the great visuals. So I'm going to show part of our demo reel. I have to ask everybody, please do not record. It's just one of those rules. So if anybody has any recording devices, you feel free to record the rest of the session, just not this part. All right, I had to cut it off there because, believe it or not, it gets even more intense and people's heads have been known to explode, which is actually the reason why we're not allowed to record, because we just can't disseminate it that widely. All right, so believe it or not, I sort of anticipated that I would have problems with getting some of the promotional material approved for this presentation. And so I came up with a backup plan. I got most of it approved. But luckily, I did have this backup plan, and I call him ambiguously heroic man. I'm going to use him to spice up the presentation in a few places where I really couldn't get the images that I want. And you'll probably see why when we get there. All right, let's get down to business. This is a synthetic image, computer generated. All right, this is from Ant-Man and the Wasp. And I kind of want to set up this problem for everybody to start understanding what it is that we do. So what does it take to generate an image like this? Now, big picture is that we have a team of artists, 50 in LA and 50 in Melbourne. And it's their responsibility to set up the parameters for simulations of natural phenomenon. These are things like light bouncing around the room, muscles flexing, skin stretching over, fascia, cloth tearing, cloud swirling, buildings falling down. So all of these types of things that we sort of take for granted as just occurring in the natural world, and on set, if you're filming, you just point a camera at it and you capture it. In visual effects and animation, we have to simulate all of these things, and these are really complex simulations, and there's many different kinds, and they have sort of their own properties. Now, so why do we distribute our computations? Well, the first and obvious one is to scale, right? If these types of simulations that we're running are very slow, we want to run them on as many machines as possible. The next reason is to move work, actually, the type of computations we're doing between our sites, so between LA and Melbourne. So one of the key things here is that LA and Melbourne each have what we call a render farm. It's really a server room full of machines that are doing compute all day long. And so we need to be able to package up work and send it either from LA to Melbourne or vice versa, depending upon the workload, right, the availability, so load balancing. And the last big reason is to leverage the cloud. Right? This is sort of a subset of the previous problem. If we know how to package up something and move it from LA to Melbourne, then we know how to move it from LA to the cloud. It's mostly related. All right, let's talk about the constraints. These are some of the things that I think are, taken as a whole, unique about our industry and set up some of the challenges of moving to the cloud. The first one is that we work on very large assets. So what does that mean? On-prem, we have Isilon, so basically, fast storage up to a half petabyte, and that's in each LA and Melbourne. We sort of mirrored infrastructure. We also have another half petabyte of nearline storage and a lot more offline storage. At any given moment, we might have tens to hundreds of terabytes of data that's actively being read or written, so really hot data of that half petabyte, of that 500 terabytes. Next up, we have long tasks. We talked about these simulations. Our task can take anywhere from 10 minutes to 10 hours, and that's for a single task within a larger job. We have, say, if you're doing a simulation, you have one task that represents work that needs to be done back to back to back to back, where each frame of that simulation is dependent on the previous frame. And what that means is that there are a lot of these types of tasks that we have that cannot be subdivided any further, right? Like 10 hours, well, let's say 2 hours is the best that we can do in that scenario. If we try to subdivide it, we hit a threshold where there's diminishing returns. And last up, and this is one that I think is really interesting, is that the work we do is heavily dependent on artists. There are manual checkpoints between each department. So think about it like this. You have an artist, they set up their simulation, they submit it to the farm to compute. They get the results back, they review it. It's not quite what they wanted. They tweak a parameter, repeat. They do that until they get it to something that can be approved and passed to the next department. And that asset becomes the input for the next department's iterations, right? And so on and so forth until we reach the end of the pipeline and we have some sort of finished result that we deliver to the client. So what that means is we have these manual checkpoints that it makes it very hard to automate when your automation always has to stop, pause, potentially for days or more, depending upon whether the artist is there, availability and whatnot. So this becomes a big challenge for automation for us. Next, we're going to talk about user stories. The constraints are sort of inherent in the system. This is more about our wants and desires in terms of how we want to manage distributed computations. So we need powerful and flexible priority management. Think about that example of an artist submitting work. We have things that we call hero frames, or you might think about them as canary tasks, something where we can get a few results back quickly and say, okay, does this look right? Yes, then release the remaining tasks. And we need to get those tasks back as quickly as possible because obviously labor is expensive. We don't want artists waiting around. And our iterations can be really long. We need to keep those cycles as quick as possible. And we also have many different types of compute machines. They have different resources available. We need a scheduler that can match up our compute resources with the types of jobs that need to be executed, along with the whole prioritization system in order to make sure that the right tasks are happening first. Next up, we need a shared file system for both our users and our compute. So a way to think about this is a lot of industries will have a large database. Right? We have databases as well, but we essentially work with our file system like a database. It's actually kind of unfortunate because file systems have many disadvantages compared to databases, but we have a half petabyte of data and we have applications which only know how to read and write via file systems. They don't know how to access buckets from the cloud and things like that. And it's also very difficult to draw a clean line between the data that an artist needs and the data that your task workers need. Python APIs for automation, this is a simple one. Pretty much every application in VFX provides these. A user-friendly UI, we talked about how this is an artist-driven process. We need to distribute and allow the artists to basically self-serve, solve their own problems, view their tasks, see what their status is, potentially requeue them, look at logs, and so on and so forth. The last point is maybe a slightly nuanced one. Our goal is primarily to orchestrate work. When we're talking about distributed task computation, things that come to mind might be MapReduce, any kind of MapReduce. We heard earlier about Netflix Archer. There are other options like Hadoop, Spark. And in these scenarios, you map across many task workers, and then there's a reduce phase where you aggregate down. So typically, that could be an example like a running average, some sort of value that's useful. In our case, there's not a reduce phase. There's not really a point where we say, hey, here's this number we got, and it's interesting. It's really all about producing artifacts, creating rendered files, caches, and things that need to be passed on downstream. So it's all about orchestration and the timing of things. Now, for us, The solution that we found to all these constraints and user stories is Deadline. It's a task management system that's made by Amazon, and it sort of answers, it's designed specifically for VFX and animation for these specific set of stories that we need to solve. One of the things that's really cool about it is that it's designed to orchestrate and help you manage your on-prem resources, but it also knows how to burst and allocate tasks into the cloud. And that's incredibly powerful. And this leads us to our next topic, which is Studio in the cloud. This is a topic which is very close to me right now because Luma is actually in the middle of moving studios. We're going to basically just move down the street, which, even though it's close by, it's an incredibly complex process. We have a lot of infrastructure that needs to be taken down and moved. And in this process, we asked ourselves, well, how large do we want our new server room to be? We get to choose. Do we want to move all of those on-prem resources over, or is this the moment where we basically say, look, we should move into the cloud? And so I put together the most complex spreadsheet that I've ever put together, doing a total cost of ownership calculation, TCO, for this. And I essentially came up with the answer that we shouldn't buy any more compute machines. Really, we have a capital expenditure on the current machines, and once those things age out, it doesn't make sense to buy any more. This graph is really the crux of that entire calculation. And this is sort of, using these numbers, which I'll go over in a moment, is how we come to our answer on the TCO, on the total cost of ownership. So what we're looking at is a graph of our on-prem resource utilization. Y-axis is percent utilized, with 100% at the top. This is, let's say, roughly 200 machines. It fluctuates a little bit over time. And so you see this sawtooth pattern. And those troughs are periods where we don't have enough work to do, right? Where we have more compute resources than we have work. Sorry, the other way around. And you can see at the very end there's this precipitous drop-off, right? That is when we delivered our latest show, which is Spider-Man Far From Home, which I think comes out in a week or two. Those little troughs represent basically weekends. So on Sundays, we usually end up clearing a lot of our backlog. You see, we didn't actually clear all of our backlog for a long period. That was because we were really busy. We had a lot of work to do. And you can see in the middle there, essentially, we went through several weekends where we didn't clear backlog at all. And so what's the problem with this? All right, well, so this is, we'll come back to our ambiguously heroic man and his mischievous brother. And trust me, the original slide was amazing. So they're trying to illustrate one of the core things here for us. So this is something that's not included in your total cost of ownership, in our total cost of ownership thing. This is one of those intangibles, because it's really hard to put a numerical figure on. So the way that we work right now is we say, all right, we have all this work queued up. How long is it going to take to get it all done? And we write tools that go through all of our historical data, and they look at the jobs that are currently queued up, and they say, well, these jobs look like these other jobs that we've done in the past, and so we make a guess at how long the whole thing is going to take. It's going to take three render days, or complete farm days in order to clear this backlog. Well, what does Melbourne look like? Let's shuffle these jobs from LA to Melbourne and try to get these things done. And even then, well, man, I don't know if we're going to get it all done in time for delivery, right? When you move to the cloud, you take that static resource and you turn it into a variable. And then you just solve for time. When do we need it done? And then you spin up as many resources as you need to get the things delivered, exactly when they're delivered, when you need them to be delivered. Next, we're going to go into cloud challenges and solutions. So essentially what this is a series of thought experiments on how to move pieces of your architecture between on-prem and the cloud, and what each of those configurations looks like in terms of pros and cons. Option one, synchronize your storage. So I'll go over the image here a little bit. On the left, we have our workstations. This actually represents about 50 users. We have our on-prem storage, 0.5 petabyte of data, as we talked about. And then in the cloud, we have cloud storage, which is a subset of the on-prem storage. Really, only data that needs to be there is what we actually need active in the cloud. That might be, say, 50 terabytes. And then we have our compute, which is scalable. We can go up and down with that as much as we need. Same with the storage as well. Now let's look at the analysis of this. Overall, the plan is pretty cheap. Bandwidth is cheap. We're doing this on a 1 gig connection right now. Storage, cheap. Well, in the sense that we have a sunk cost. We've already purchased the on-prem storage, and 50 terabytes of storage in the cloud is not particularly expensive. Egress, so we have to pay in order to get data from the cloud down back into our on-prem, and essentially I put an asterisk there because it scales with the amount of work that we need to do. And limiting factors here are bandwidth. In terms of synchronizing data to the cloud and back again from the cloud, there's obviously scenarios where if we try to scale compute too much, we can't get all of the work back, or we even feed it with all the assets that it needs to do its job. This is predominantly how we work in the cloud right now. So one of the things, if I can jump back real quick, if you look at this graph, in some of these periods where we hit peak and we're basically maxed out, we can take, and the way that we work now is we take that overload, that overflow, and we put it in the cloud. It's what we call bursting to the cloud. So we use cloud in a strategic sense, and we only end up using it maybe 1 or 2 times a year right now. With option 2, it's very similar to option 1, but what we've done is we simply remove the cloud storage. We take that away, and instead we take the compute and we directly mount our servers. This is only possible if you have a very low latency connection, something like you would have between LA and San Francisco. And in that case, like if you have direct connect, you can get the latency even lower. In order to do this, so we have to have low latency, we also have a lot more bandwidth. In the case of the synchronization, we can basically have jobs that prep, essentially prime the pump. We can get all the assets up there, and then the instances start up. But in the case, in this direct mount scenario, we need enough bandwidth to handle our peaks, not just the average load. We need peaks. So if all the machines decide they're going to start reading some enormous asset at one time, we need to make sure we have enough bandwidth that they can all do so. Because if they don't, then we're hobbling our very expensive compute machines. Let's look at this. So bandwidth, we have to spend more. We talked about that. Potentially 10 gigs, 4 gigs, 40 gigs. It really depends on how many machines we're going to run. Storage, again, sunk cost. Egress, again, scales with how much work we want to do. One thing to point out here is that option 1 and option 2 are not mutually exclusive. And we've used both of these options in tandem. Essentially what you might do is carve out a certain amount of your bandwidth for your direct mounting scenario. And the reason the direct mount scenario is so attractive is it lets us work exactly the way we do now. We're basically just treating those cloud compute resources exactly like our on-prem resources, meaning that as soon as we submit a job, they can start. There's no sync. As soon as they start producing results, we can look at them. There's no need to sync back. But like I said, we can still take, say, 1 gig of our bandwidth out of 10, let's say, theoretical, and use that for doing syncing to the cloud. So we might maybe send work over the weekend to maybe 500 machines while we're using just direct mount just during the weekdays. And that would let us take advantage of cheaper compute resources in different locations, right? Not be bound to the things that have the lowest latency. Next up is the cloud native option. So here, we've taken all of our resources and moved into the cloud. Compute is still there. We've moved storage from on-prem entirely into the cloud, and our workstations have moved to the cloud. And our connection between our workstations, and remember the blue represents about 50 artists, our connection from our workstation to our artists is a zero client, PC over IP. And so obviously the big advantage of this is we've taken all of our resources and made them completely elastic. Our computers are elastic, our workstations are too. I mean, so one thing to point out about the visual effects and animations industries is that they're very nomadic. We might, when we're working on a show, we might scale up by 30, 40%. And that means we need to find more workstations for those artists. In this scenario, we can easily just provision them a handful of each of them a workstation for during business hours. Now let's look at the pros and cons. Bandwidth is incredibly cheap. The amount of bandwidth it requires to synchronize 50 times 2 because we use dual monitors. PC over IP streams is not much. Storage cost is a lot. This is one of the big factors here. A ½ petabyte of storage in the cloud, if you've looked it up, is pretty expensive. Let's just estimate it at $500,000 a year. So that's one of those problems that we'll be looking at. Can we optimize that? How can we reduce the cost of that? What does the total cost of ownership look like for that against on-prem scenarios where you're having to buy hardware, do tape backup, and all those things which are a real pain in the butt. All right, next up, we're going to talk about our experiences using AWS on Spider-Man Far From Home. First takeaway is that deployment was incredibly easy. We were able to get up and running very quickly using all of AWS's APIs. We're coming from using GCP for burst rendering for the last few years. They were the first ones to be approved by Marvel and Disney for doing cloud rendering. And so a lot of our takeaways sort of are in relation to GCP. And one of the big takeaways was that it was much, much easier to configure our infrastructure. Route 53, something that our DevOps engineers could not stop raving about. It just allowed us to seamlessly integrate DNS between our on-prem resources and our cloud resources, sort of acting like a traffic cop to just say, hey, if you need these resources, they're over here and going in either direction. The other thing, stock images were incredibly easy to customize. In GCP, essentially, we have to resort to making custom images for pretty much any type of change that we want to make. In AWS, we can use DHCP option set, instance user data, a host of different features that allow us to just customize things really easily without having to resort to custom images. And the last thing that was really interesting was that we discovered that the CPUs were actually much, much faster. We were comparing 72 core machines in GCP versus AWS, and we found AWS's CPUs to be about 30% faster. And that was for the C5s. Now the future. We talked about, these are some of the things that I would love to really cooperate with AWS on over the next few years and see where we can go with these kinds of problems. We talked about how we use our file system like a database. I'd love to see a kind of globally distributed and federated file system, something that works more like a NoSQL file system. If you've heard of Ceph OS, it works kind of like this, where you have multiple locations and your files are actually being transferred between those locations. If you view your file system any particular location, you can see the full list of files, all the metadata, you can ls and stat them. Even if the files don't exist there. And as soon as you start reading, they get pulled from wherever their home is. So that would include things like rules for region tenancy. In other words, hey, I want this file to be in at least 2 locations, or one of them needs to be the cloud. Another option would be storage. Another really important thing is storage based on access time. So right now we can do, storage tiering, right? We want our data to move from fast SSD to slow spinning disk, nearline, cold line, glacier, deep glacier, right? We want them to be cascading through there, and we want that to happen automatically. But ideally, especially at those top tiers, we want it to be based on access time, right? Just because a file is 5 months old doesn't mean it's not useful. If something accessed it yesterday, then it's definitely still useful. And this gives us a kind of LRU, least recently used cache. Another really interesting option would be using machine learning. We've already, to tag images and other data for search. We've already heard from NFL folks about how they're doing things like that. And another really interesting use for machine learning, we talked about how we have all these different jobs and different types of compute resources. I think it would be an incredibly solvable problem to look at using machine learning to choose the right instance for the type of task that needs to be done. So we have all of this historical data about that allow us to predict how long, or within reasonable amount of error, how long a particular task will take. In addition, we should be able to try to guess how, what does its performance profile look like of this job? How much CPU, RAM, and I/O is it going to need? Because not every job is made the same. Some things are going to be RAM intensive, some will be CPU intensive, some I/O intensive, and usually not all 3. So those are types of problems that I'd love to start tackling in the next year or so. And so that wraps it up. Thanks a lot. I really appreciate taking the time. I hope you guys learned something. And feel free to email me.